Okay, let's get started. So been looking at in the last class. We looked at the stress state around an edge dislocation, right? So we've seen that when you have an extra half plane in the region that if you have this particular plane above this region, above this plane, you will have a state of compression. Below the dislocation, you have a state of tension. And typically, you please notice this representation which is written like that, and that is the representation for a dislocation, and this is typically called an positive edge dislocation. And if you want to represent a negative edge dislocation, then that will be that one. So this is positive, that is negative. It basically tells you that you have an extra half plane above this and you don't have an half plane below. Here it says the other way around. Okay, so this is the representation. If you are looking in the material science textbooks, you will also always see this representation, and that actually is representing an edge dislocation like that. Okay, so typically in a material, if you have an edge dislocation and screw dislocation, so they will create sort of a stress state around the dislocation core. This is what we call dislocation core. Around the dislocation core, you have some stresses induced because of the presence of this foreign half plane, which is not supposed to be there. Otherwise, it would have been a perfect crystal, right? Because of the introduction of this extra half plane, you are inducing stresses around the dislocation core. All right. So this state of the stress is going to be compressive in the region where you have an extra half plane, and the tensile in the region where you are having the absence of an extra half plane, right? And typically in edge dislocations, you will have this state of stress induced by the presence of the dislocation is either tensile. So you will have the tensile state of stress, compressive, as well as shear stress, shear strains created by the presence of this dislocation. Whereas in screw dislocations, you will only have shear strains. Okay, and so this shear strains are what is going to cause lattice distortions. When you have a dislocation, you will see a lattice distortion is caused by these shear strains. All right. So now, what are the different characteristics of these dislocations? Suppose if you have two dislocations which are of same sign. What do we mean by same sign? So here you have, this is one dislocation, this is another dislocation present in the same crystal lattice, but both of them are of the same sign. That means both of them are here positive edge dislocation. That means extra half plane is only available above this, and below the extra half plane is absent, right? This is what we term as positive edge dislocation. It is a terminology that we are adopting. Okay. So now if this is the sign of the dislocation, if both the dislocations are of the same sign, both are positive or both are negative, then when during the application of shear strain or shear stress on the material, the dislocations move within the crystal lattice. That is what we have seen yesterday, right? When they move, and if two dislocations of the same sign encounter each other, they repel each other. Why would they repel? We will see in a moment. So the same sign dislocations repel, and the opposite signs dislocations attract. So what happens when you have two opposite signs? They come together and they annihilate the dislocation. Then this is one extra half plane, and this is another extra half plane, and these two are moving together, and then you will have a perfect crystal lattice. That means you have annihilated the dislocation which was present otherwise. Because of their opposite signs, they are attracting each other, and as a result, you got rid of the dislocation in the crystal lattice, right? So the same sign dislocations repel each other, opposite sign dislocations attract each other. So that means in a crystal lattice, when these dislocations are moving, as we have discussed, it is very likely that in a crystal lattice you would typically find several dislocations, right? And all these dislocations, when the crystal lattice is subjected to external stress, then these dislocations tend to move, and because of the fact that they are moving and depending upon their signs, it is possible sometimes that the dislocations annihilate, or they may actually interact without annihilating. They may actually repel each other, or they may do something else, right? So that means in a crystal lattice you can expect interaction of these dislocations, and when you are when you are subjecting the material to an external stress, then you are through that, if you are imparting plastic deformation to the material, during the plastic deformation the dislocation density keeps on increasing. That means you are generating more and more line defects, right? So the density typically of a deformed metal is 10 power 10 per mm square. It's actually mm per meter cube per mm square. So 10 power 10, sometimes people also tend to think that as 10 power 10 dislocations per mm square of area, but the right way to define this is the total length of the dislocations, so 10 power 10 mm length in a volume of cubic millimeter material. That is the real meaning of the dislocation density. And because of the presence of the dislocations, as we have discussed, you are going to alter the strain field around the dislocation core, right? You have a local tensile state and the compressive state. That means you are actually modifying the local strain field around the dislocation core, and that might lead to something called strengthening mechanisms, which we will see either today or in tomorrow's class. Okay? So the point that we are trying to make here is that in a crystal lattice, you are going to see several dislocations, and these dislocations are bound to interact with each other, right, when you are applying external load on the material, right. That is something that is very important to note down. All right, and then we will introduce the concept, concept called slip systems. And in the previous lectures, when we have discussed the structure, crystal structure, we have discussed something called closed packed planes and closed packed directions. And at that time, I have told you that it is important to know these closed packed planes and closed packed directions, because they have an implication to the deformation in materials, and that is what we are going to see here. So as we have discussed already, the plastic deformation in a crystalline material is actually due to dislocation motion, right? Slip of crystal planes is basically due to dislocation motion. And how do these dislocations move? So dislocations prefer to move in certain planes in certain directions. That means they have some preference. They try to choose some preferential planes, and in those preferential planes in some preferential directions. If they are not available, you might have to do additional work in order to make them move, but if at all there is a preferential plane and a preferential direction that is available, then the dislocations tend to move in those planes in those directions, right. So the slip system is actually a combination of the planes in which slip can take place, that means the preferential plane, and the directions in which the slip can take place. So the slip plane and slip direction together is called slip system of a crystal structure, of a crystalline material. Okay? So obviously the slip system depends on the crystal structure, because there are the preferred planes and preferred directions, or the slip plane and slip direction are not necessarily the same for different crystal structures. For FCC material, it is going to be different, and BCC material, it is going to be different. Why is that? The dislocations choose to move in certain planes and certain directions, such that they cause as minimal atomic distortion as possible to the crystal lattice. So they choose their planes in such a way that the motion of the dislocation happens without actually causing too much of a distortion to the crystal lattice. Okay, that is the principle. So if it has to do that, if the dislocation has to move without causing too much of a distortion to the crystal lattice, what it has to do? It has to move in closed packed planes, and in those closed packed planes in the closed packed directions. So let us see here. So, here you have this is close packed plane compared to this guy, right. So, now let us say this is one plane of atoms, this is another plane of this is 1, 2, 3, 4 are one plane of atoms, and Roman numbers 1, 2, 3, 4 are another plane of atoms, and then you are applying the shear stress on this lattice. Okay. Then what happens after slipping by one interatomic distance? This atom, Roman number 1 atom, after slip has occupied the position of this atom in this structure. This is before slip and this is after slip, right. This guy has moved here, if you carefully look at it. So, what is the, so that the distance that it is moved, that means the amount of slip that happened was how much? That was the slip, right, and that is equal to the diameter of the atom, right. The interatomic distance is equal to the diameter of the atom, isn't it? So, the Burgers vector represents the direction and magnitude of the slip, that is what we have discussed in the yesterday's class. So, the Burgers vector in this case is d, d is the diameter of the atom. And now, the energy associated with movement of this dislocation or causing to cause the slip is proportional to magnitude of the Burgers vector square. So, square of the magnitude of the Burgers vector, square of the magnitude of the Burgers vector. All right. So, now this is a closed packed system and now this is not a closed packed system. Now, let us see what happens in this structure. Now, if you are causing slip, then what happens? The atom, Roman number 1 atom has occupied here the position of Roman number 2 atom. And now, the amount of distance, that means the Burgers vector is equal to square root 2d, isn't it? So, it has to move a longer distance, and hence again the energy associated with that is proportional to square of the Burgers vector, and that means it is proportional to, that is equal to, that is approximately scales with 2 times d square. That means in this case you need to spend more energy compared to this case. Is that clear? So, here because b equal to d, then this will be d square and this is 2d square. And so, by moving in the closed packed direction, you are actually spending less energy, and hence obviously dislocations prefer to move in that direction if at all they are available. And now coming to why do they, so closed packed direction seems to be fine. Why do they try to move in closed packed planes? So, here this is a closed packed plane, it is not a closed packed plane, right, the bottom one. And now, if you see the interplanar spacing between the closed packed planes is largest compared to all other planes. This distance is largest compared to this. And on the top of that, if you carefully look at the movement of, let us say this is atom 1 and this is atom 1. In both cases after slip it has to go and sit here, and here this has to go and sit here, right. So, if it has to do that, here it will cause much less distortion compared to here, right. Here it will cause much higher distortion compared to here, and here it has to overcome a larger hill in terms of energetics compared to here, right. So, that means if you are moving in closed packed planes, because of the fact that the interplanar spacing is larger, you are going to cause much less distortion to your crystal structure, right. And that is the reason why dislocations prefer to move in closed packed planes and in closed packed directions. Okay. So, the dislocations prefer to move in closed packed planes along closed packed directions as the interatomic spacing in the plane is small, that means interatomic spacing within the plane is small in the closed packed direction, and as a consequence the interplanar spacing is larger, which eases the atomic motion without actually causing lot of distortion to crystal structure. Is that clear? Why dislocations move in closed packed planes in the closed, and in the closed packed planes they prefer closed packed close packed directions. All right. So, what are the different kinds of slip systems that we can observe in materials with different crystal structures? Right? In FCC material, we have already discussed in the previous lectures that 111 plane is the close packed plane. So, what is this? What does this represent? It's a family of 111 planes, right? Curly brace means family of planes. So, all the family of 111 planes are your close packed planes. In the 111 plane, family of 110 or 110, this is family of directions, right? This is the slip directions, family of slip directions and family of slip planes, right? How many such planes are there in FCC, in one FCC unit cell? How many such planes? Yeah, louder. So, she thinks 4. All of you think 4? Non-parallel planes. All other planes parallel, so it should not be considered. So, you will have only 4 non-parallel planes. Okay? And in each close packed plane, how many close packed directions are there? If you see your FCC, that is your close packed plane, isn't it? And this is one close packed direction, this is another close packed direction, that is another close packed direction. So, how many? 3 close packed directions, 4 close packed planes, and hence you will have total of 12 slip systems. FCC has 12 slip systems. So, dislocations can choose to move in any one of these 12 slip systems in FCC, and typically most of the ductile materials that you find are in general FCC in their crystal structure, and BCC has the close packed plane 110, 211, 321, all of these are close packed planes, family of planes, and the close packed directions, and in total in BCC you will have 48 slip systems. And again in HCP, this is HCP, and you have 12 slip systems. Okay? So, 0, 0, 0, 0, 0, 0, 1 is what? Which plane is that? In HCP? 0, 0, 0, 1. What is the name of that plane? Basal plane, right? Because it's the base, so that is why it is called basal plane. And in that plane, 1, 1, 2 bar 0, we have seen that that is the close packed direction in one of the classes, right? So, totally you have one plane, 3 directions, you will have 3 slip systems, and again you have other close packed planes and close packed directions. So, total you will have 12, but these are easy glide planes. So, 3 is most prominent slip systems in HCP. So, but we know that the plastic deformation is much easier in FCC materials compared to BCC and HCP. Okay? But you can clearly see that there are more number of slip systems in BCC. There are 48 slip systems, 4 times the number of slip systems that are available in FCC. If there are more number of slip systems that are available, naturally you would expect that material to have easy plastic deformation. That means the dislocations can always find one of these slip systems to move in. So, the plastic deformation should be easy, and hence they should be ductile, more ductile. But it turns out that if you take steel, mild steel or plain carbon steel and aluminum, aluminum is known to be more ductile compared to steel. Agreed? Right? So, we know that steel at room temperature you can have the crystal structure is BCC. So it is not as ductile as aluminum, and there are several materials which also tend to be much less ductile compared to FCC, both in BCC structure and HCP structure. Although the number of slip systems in BCC are much larger in number. Why is that? So I will not answer that question. I will leave it to your research after the class, and then we will discuss that particular aspect, why FCC, the materials with FCC crystal structure are more ductile than BCC material in general. Okay? All right. So in each of these materials, the Burgers vector represents the direction and magnitude of the slip, right? So the Burgers vector usually is denoted by B, that represents the dislocation slip direction and the magnitude. And the magnitude is usually equal to unit slip distance or interatomic separation in the direction, depending upon the interatomic spacing in the close pack direction. So in FCC, what is the close pack direction in which dislocations prefer to move? 110, right? 111 is your close pack plane. In that plane, 110 is your close pack direction. So the Burgers vector is A by 2 times 110, and like that BCC and HCP, you please go back and verify these formula, how you would get this equal to. Basically, Burgers vector represents 1 unit slip distance. That means the interatomic spacing between interatomic spacing in that particular crystallographic direction. Okay.